Welcome, everybody. It's my pleasure to have everybody show up today for the 2014 Daniel and Irma Evans Lecture. I always like to point out that even though there are many Daniel Evans, Daniel Evans, former governor and senator, set this up, but it was done in the name of his father, who is an eminent civil engineer, graduated in 1918, was it? 17 from our department. So we have a long history and line of civil engineering Evans people, which is great. And so this lecture was set up, I think in early 80s, was it? It's been a while. And the genesis or the idea behind this series is that as students and as faculty and even as alums, we live in a relatively narrow tech-driven world. The classes those of you students have, we as faculty are always kind of hammering on the math and the science. And a very important thing that we often give lip service to, but I think this lecture tries to very much emphasize, is the fact that we live in a very complicated world, and if you want to be really an effective and successful engineer and have a broader impact beyond just the technical side, you really have to learn and understand policy, economics, just the broad sociology, the broader way in which systems and people and organizations work. And so we've had a long string of eminent people who have come in and spoken from various perspectives, but in general to give a broader view of the engineering context in which we work, or in which you're studying, in which you will work. So today our speaker is Mark Jacobson, Mark Z. Jacobson. Now around Seattle in particular, Jacobson's a very common name, so it's good to have an uncommon middle initial, right? Otherwise you'd be hard to Google yourself, I suppose. And Mark is a faculty member at Stanford University, and I think it's interesting that if you just look at his degrees, he kind of embodies the idea of what the breadth that we try to bring to this. He has degrees in civil engineering, in economics, in atmospheric sciences, and I guess 2 in atmospheric sciences. Yeah, civil, economics, environmental engineering, 4 degrees, count them, okay? And from a broad variety of fields. He's officially professor of civil engineering or environmental engineering at Stanford. He's also the director of the Atmosphere/Energy program, which sounds pretty cool and will be part of what I think we're here about. He's senior fellow at the Wood Institute for the Environment and is also senior fellow for the Precourt Institute for Energy. So he must have a big business card, I imagine, among other things.
Small print.
Anyway, we're very happy to have you here, and we look forward to your talk. Please join me in welcoming Mark Jacobson.
Thank you for that kind introduction, and thank you, the Evans family, for supporting this talk, and also the Department of Civil Engineering at University of Washington. I'm really happy to come here and talk about how Washington State and the other states in the United States can change their energy infrastructure for all purposes to one powered by wind, water, and solar. And all purposes means electricity, transportation, heating and cooling, and industry. And so why do we want to do this, or why do we care? And everybody has their own opinion about why you might want to change, and some people don't want to change. But from our point of view, we look at it from 3 major points of view: air pollution, climate, and energy price stability and energy stability. And from an air pollution point of view, 3 to 7 million people die prematurely each year from air pollution worldwide. And half of that's from indoor air pollution, half is from outdoor. And so it's the leading cause of environmental risk, death in the world. And 20% of these people are children under the age of 5 years old. Most of those are in developing countries who perish from complications from asthma, respiratory illness, cardiovascular disease, but also pneumonia that's brought on by reduced immune system problems associated with air pollution. And so it's a very avoidable cause of death. In the US, there are about 60,000 premature mortalities per year. And this costs the US on the order of 3% of the GDP. It's about $530 billion of cost for not only the mortalities, but the millions of people who are injured from asthma and emergency room visits, from the cardiovascular disease, respiratory illness, lost work days, lost school days, higher insurance premiums, and higher workmen's compensation rates, higher taxes that result from all this, this mortality and morbidity. And so this is one problem we want to solve, and almost all of this is due to the combustion of fossil fuels and biofuels. And then a second major problem is global warming. And I'm not going to go into that in detail except to say that temperatures today, or the rate of change of temperatures, higher than any time in history. Temperatures have been higher in the past, like 100 million years ago, temperatures were higher than today, but nobody lived on the Earth. And in fact, 4.3 billion years ago was referred to as the Hadean period because the Earth was molten. So we have had higher temperatures than today, but we didn't have 7 billion people living on the Earth. And so if we melt all the ice on the Earth, which is about 70 meters worth, mostly in the Antarctic, then we would flood 7% of all the land worldwide. And most people, 80% of populations, live along the coast. So that's just one problem associated with global warming. And just the other day, it was learned that the West Antarctic ice sheet, which is about 10% of the total Antarctic ice mass, is almost certainly going to melt. That's about 4 meters of sea level right there. The Arctic sea ice is about to melt within 10 to 30 years, and that could trigger a positive feedback because it's very reflective, and if you melt the Arctic sea ice, you uncover the dark ocean below, and that allows more sunlight to be absorbed and heats the ocean even faster, triggering a positive feedback that may accelerate warming and melting of the Greenland ice sheet and causing warming throughout the Earth faster. Now, other impacts of global warming, of course, are greater air pollution, because higher temperatures increase air pollution where the pollution is already bad, and due to chemical reactions that are sped up due to higher temperatures. You have greater heat stress and heat stroke of people who live in places that are already hot, and this will be an additional source of mortality and an additional potential famine, especially in places like sub-Saharan Africa, which are already hot and people are already on the edge. You would also have more extreme weather, more severe storms, greater intensity of hurricanes, more severe occurrences of tornadoes, and greater heat extremes both in the positive and negative direction. You'd also have shifting of agriculture, greater influenza and malaria, which are temperature dependent, ocean acidification, where in coral reefs, more coral reefs will die out. There are many impacts of climate change, and as I'll indicate, the problem is much worse than people think, and I'll show why in a few minutes. The third problem is the fact that energy prices are going up gradually because fossil fuels are limited resources, so you have to mine and fuel, you have to mine them and transport them, and so not only is there a lot of labor costs associated with that goes up over time, but these are limited resources because when their supplies diminish, their costs go up. And so if costs go up sufficiently, then you'll get energy price instability, and that leads to eventually economic and social instability. Eventually would lead to chaos if nothing else was done, in civil war, etc., if prices got too high. And we'll see that if you go to wind and solar power, for example, which have zero fuel cost, you stabilize the price of energy, and so you avoid this potential problem. And because populations are growing and energy demand is increasing because many developing countries are becoming more developed, this is a growing and severe problem. So we need to be able to stabilize energy prices and prevent further global warming and eliminate air pollution mortality, which drains society of a lot of resources. Just to give an indication of, it looks here in Washington State, the pollution is not bad, only a few hundred mortalities per year due to air pollution, premature mortalities. But in Beijing, China, this is like smoking 2 to 3 packs of cigarettes a day. And this is from 2013. It looked the same in 2014 in January. But most countries of the world, most big cities of the world have severe air pollution problems like this. And this is what, in China alone, about 1 million people die prematurely each year from air pollution. As I mentioned, in the US, it's on the order of 60,000. In Europe, it's around still 300,000 people per year prematurely. But India is almost about 800,000 or so. So we've got this severe pollution problem, but these are the lungs of a teenage non-smoker who lived in Los Angeles, who died in a car crash in the 1970s. So living in Los Angeles in the 70s was like smoking 2 packs of cigarettes a day, just if you're an innocent child. And even in the US, if you live in a big city, your average lifespan is about 6 months less than if you live outside of a city because of this pollution problem. Now, just one more comment on climate, then I'll get into really the solutions. If we look at net global warming, which is about 0.8 degrees Celsius since the middle 1800s, and that's the right bar, represents a warming of net observed warming of about 0.8 degrees Celsius. That's really due to a combination of warming due to greenhouse gases, which is the left tall bar, which is over 2 degrees Celsius. So if you just imagine that if all we considered was the greenhouse gases, the Earth would be about more than 2 to 3 times warmer, or the change of temperature due to global warming would be 2 to 3 times greater than it has been. But there's an additional warming due to fossil fuel and biofuel soot, which is black and brown carbon, usually the stuff that comes out of diesel exhaust or burning solid biofuels. It's when you see brown smoke in the air or black smoke, that's because it's absorbing sunlight and heating the air as a result directly, which is different from a greenhouse gas, which takes infrared radiation from the surface of the Earth that's being emitted by the surface of the Earth and traps it near the surface. Particles, soot particles, directly absorb sunlight and then convert that sunlight into heat that they radiate around them. So heat the air directly, but these particles are also the deadliest components of air pollution. But there are also other particles that we call cooling particles that are similar in terms of their health impacts. They also kill people, but they are more reflective. So the lighter colored particles that are white or gray, or particles that swell due to water going on them, they become whiter colored. They cause a lot of cooling, not only because they directly reflect light, but because they enhance cloudiness, because the clouds get spread over more particles. And as a result, when you have a greater number of smaller drops compared with a smaller number of large drops with the same total water mass, you actually get more reflection with the greater number of smaller drops. And so when you have more air pollution particles in the air, they increase the cloudiness, increase the reflectivity of the cloudiness. So that's what the cooling particles do. They increase cloudiness and they increase reflectivity. But the point I want to make here is they offset, they mask or hide about half of all global warming. So as you clean up air pollution, you're unmasking or unhiding half the global warming that's occurring, and you basically double the amount of warming. And without, this could happen rapidly because particles can be removed pretty fast from the air if you stop emitting them. But we want to do that because these particles are what causes 90% of all the health problems associated with pollution. So one strategy could be, well, you can focus, I should mention the particles have a lifetime of anywhere from a week to a few weeks in the atmosphere. You stop emitting them and then they'll come out of the atmosphere relatively quickly, although they have feedbacks that last a few years. But greenhouse gases last decades, while some are, like methane, last 1 decade in terms of its lifetime, whereas carbon dioxide is about 5 decades, around 50 years. So that once you put them up, they stay up there for a long time. And if you try to stop their emissions, what's in the atmosphere will have an impact for a long time. Whereas the particles, you take them out, and their impacts are felt immediately. So if we took out just the soot particles, we would actually get a rapid cooling, short-term cooling of the climate. And that could be one way to save the Arctic sea ice. But in reality, you really need to change, because global warming, the greenhouse gases are building up, you really need to control the greenhouse gases and the soot, and you want to control the air pollution particles that are causing health problems, so you need to control the cooling particles as well. So you need to ratchet down all those pollutants. And that's really what I'm going to be talking about. How do you change, in order to do this, you need to change the energy infrastructure. Instead of using combustion, because that's what's causing all this pollution, you need to go to a non-combusting energy infrastructure. And so let's talk about how we can do that. So a few years ago, we did this review of different proposed energy solutions to global warming, air pollution, and energy security, and came up with a ranking for the electric power options and transportation options. And this ranking does not reflect, like what's not recommended here does not mean that this is not better than what we have today to some degree. It just means it's not so good as the recommended options. But the recommended options were recommended because they had the best benefit in terms of reducing pollution, reducing climate problems, using the least amount of land, reducing water use, reducing catastrophic risk, and increasing reliability, and a few other factors. But what was recommended for electric power were wind, concentrated solar power, CSP, which is where you focus light off of mirrors to a central tower receiver to heat a fluid. The fluid can then be stored at night, and then when you want to use that fluid, you run it by water to heat the water to generate steam, to run a steam turbine to generate electricity. So this is a way just to use basically concrete and steel and to generate electricity from sunlight. And so that was ranked very high. Geothermal power, where you basically pump water down a one hole, down to hot rocks, heat the water, it comes up the other hole, and then you have steam that runs a steam turbine. That's geothermal power, and there's other types of geothermal as well. But tidal power, which is basically wind turbines under the water. Photovoltaics, which is your typical rooftop solar, or it could be in power plants. Wave power is basically you take advantage of the up and down motion of waves. The mechanical energy, convert that into electrical energy to generate electricity. And then hydroelectricity, which you're all very aware of in Washington State. But what was not recommended, and I'll explain why in the next few slides in more detail, were nuclear power, coal with carbon capture, natural gas, or biomass. So I'll save that for the next slides to explain why. Then for transportation, using these wind, water, solar options for driving or for powering battery electric vehicles or for producing hydrogen for hydrogen fuel cell vehicles were deemed the cleanest ways to move forward for transportation. But what was not recommended were liquid biofuels such as corn or cellulosic or sugarcane ethanol or soy or algae biodiesel or compressed natural gas. And and I'll explain also why in a minute, why those weren't. But I want to just point out one thing. In terms of the liquid biofuels, you're still burning them. They still produce pollution about the same amount as gasoline or diesel. And so from an air pollution point of view, it's about the same. And from a climate point of view, corn ethanol, depending on how you grow it, there's a lot of energy that goes into producing the corn. That's from fossil fuel driven, and also cellulosic ethanol and the other ethanols. So you may reduce or increase actually the total carbon emissions depending on how it's actually done. But it doesn't come close to reducing the carbon as you would with, let's say, a wind turbine powering a battery electric vehicle where you get 99.8% reduction in pollution and carbon. And anyway, I'll explain these in a little bit more detail. So why not natural gas? Well, first, we're not comparing it. Every new natural gas plant that is put up today is going to be there for basically 40 to 60 years. So it's not really a bridge fuel. It's really a permanent infrastructure that will be there a while. But it does put out 50 to 70 times more carbon and pollution per kilowatt hour generated than wind energy. So it's an opportunity cost as well. If you're spending $1 on gas versus $1 on wind, you're putting up a lot more pollution per dollar that you put up for gas versus wind. Air pollution alone from natural gas mining and transport and use causes 5,000 premature deaths in the U.S. And that's a little less than 10% of the total death rate is due to natural gas production and use in the U.S. Methane from natural gas, which is mostly from leakage, because methane is the main component of natural gas, is one of the main contributors of Arctic sea ice loss, as is the black carbon from gas flaring. And when you hydrofrac gas, which is spraying water laced with chemicals under high pressure to crack rock, you actually release even more methane because the leakage rates are higher, partly during the drilling and partly due to when you put cement casings in. There are tens of thousands of natural gas hydrofrac'd wells spread out over the U.S., and 5% of all wells ever built leak immediately, and 50% leak over their lifetime. So you can imagine there's spewing natural methane from these wells during different phases, and when there are a lot of flyovers among these wells, these flyovers indicate high levels of methane, much higher than emission inventories used to indicate. So this is now becoming more well known as a serious problem. But even without the additional leaking due to hydrofracking, the methane from just conventional gas leakage is a significant problem. Well, why not what's called clean coal, or coal with carbon capture and sequestration? That's where you take the CO2 from a coal-fired power plant exhaust stream and you pump it underground into a cavern. And that would reduce about 85 to 90% of the CO2 emissions from the stack, which sounds good, but you do not reduce any of the emissions from the mining or transport of the coal. In fact, you need 25% more coal to run the carbon capture equipment, and this requires 25% more mining. And you also do not reduce any of the emissions associated, other emissions aside from CO2 associated with the coal. So these all increase 25%. So you actually have about 50 times more CO2 per kilowatt hour generated than wind with coal with carbon capture, compared with when you have, which is less than, well, for the pollution, it's 150 times more CO2 per kilowatt hour. And the carbon capture equipment, if you don't have that for normal coal, you get about 150 times more CO2 per kilowatt hour than wind power. So what about nuclear power? Because people say, well, that's really clean, and we should use that. But actually, it's not clean, because you need to continuously mine and refine uranium during the lifetime of a nuclear reactor. And there are 2 coal-fired power plants in the U.S. whose sole purpose is to refine uranium for nuclear energy and weapons in the U.S. And if you account for that and not only the construction of the plants, but also the fact that it takes about 10 to 19 years between planning and operation of a nuclear plant, including the permitting time and construction time, compared to about 2 to 5 years for a typical wind farm or solar farm. While you're waiting around after that 2 to 5 years, you could have put up the wind or solar farm. For the nuclear plant to go up, you're running the regular electric power grid, which is mostly coal and gas. So when you account for those 2 factors, there are about 9 to 25 times more emissions per kilowatt hour generated from nuclear than wind power. And in addition, as you all know, there are 1.5% of all nuclear reactors ever built to date, and there have been 440, have melted down to some degree or another. Actually, it's more than 1.5%. And 5 countries of the world have secretly developed nuclear weapons under the guise of civilian nuclear energy programs. So there's a risk with nuclear energy. If we power the entire world with nuclear in 2030, we would need 16,850 megawatt nuclear plants, and we have about 440 today. So even if we went to 800 plants, that would double the number. That would only account for 5% of the world's energy. But more countries of the world would have the capability, or might seek the capability, to develop nuclear weapons. So this is a risk that may or may not come to fruition, but there is no risk with solar or wind, or geothermal for that matter. So this is just one more thing in the equation that we want to consider. And then there are also unresolved waste issues. Now, if we look at areas, now biofuels are pretty popular, but let's just look at how much area it takes to power anything with a biofuel. Because you'll see that it's really impossible on a large scale to use biofuels for large-scale energy. So if we want to power the U.S. vehicle fleet, the on-road vehicle fleet, with cellulosic ethanol, this is the land area that would be needed. It's equivalent to about 20% of the entire United States, including Alaska. Now, if we wanted to do it with corn ethanol, it's about 14% of the entire U.S. And now there's a range of uncertainty here, and there's less uncertainty with the corn ethanol because it's been implemented more. But it's still 14% of the U.S., including Alaska. That's about the size of this dot. Now, if you want to do it with nuclear, it's not one of its big problems. It takes up about the size of Rhode Island. So you can sacrifice Rhode Island for the vehicle fleet. Now, with wind power, there's 2 areas of interest. One is called the footprint area, and the other is the spacing area. The footprint area is the land on the ground that's actually taken up by the turbine tower and the cement around it, and you can count roads if they're paved, but usually they're not paved. They're mostly just grass or just dirt. And then there's a spacing area, which is a space between wind turbines that can be either open space or farmland or rangeland or agricultural land, or could go over the ocean. So to run the whole US vehicle fleet, you need about 78,000 to 143,000 5-megawatt wind turbines. So around 100,000 large wind turbines. And that would take less than 3 square kilometers of land on the ground is the footprint in terms of the tower area and the cement around it. But it would take about half of 1% of the land area for the spacing. So that's about almost 1/30th the land area for corn ethanol to do the same thing. And this is to power battery electric vehicles versus corn ethanol running what are called flex fuel vehicles on E85, 85% ethanol and 15% gasoline. Now, a lot of this could go over the ocean as well, as we'll see. But solar, which is down in Florida here, and that takes up about 1/3 the land area of wind for spacing to power the whole US vehicle fleet. I mean, that dot in Florida would power the entire US vehicle fleet. Now, geothermal even takes less area, but we don't have as much geothermal resources. But it's that little dot, so that would take even less spacing area compared with wind or solar, but more footprint than wind. So wind, geothermal, solar, they all don't take up a lot of area. And I'll show you a lot of maps with areas in a minute to see, well, what if we want to power the entire US for everything? But you can start getting a picture. But this is another reason why we would never, you can spend all the money on ethanol and biofuels you want, but you're just never going to overcome this problem. Photosynthesis is only 1% efficient. So only 1% of sunlight will can get possibly converted to energy by growing things. If you take that same land, you put a solar panel, solar panels are like 20% efficient. So you're going to immediately get 20 times more energy per unit land area, and even more because the photosynthesis is less than 1%. So it could be up to 80 times more energy per unit land area by putting solar panels on the same land as biomass. So instead of growing biomass, why not just put solar panels there? You get between 20 and 80 times more energy. Or you can take 1/20th to 1/80th the land to get the same energy. So let's look, though, can you then take all these wind, water, solar options and power the entire world in individual states with these energy options? So worldwide in 2010, the end-use power demand was almost 13 terawatts, or trillion watts of power. And in 2050, that's expected to grow to 22 terawatts. But if we convert to electricity and hydrogen for everything, we actually get a power demand reduction of 30%. And this also accounts for some end-use energy efficiency improvements and people changing some of their habits. But actually, we're very conservative here in end-use energy efficiency. Of that 30% worldwide reduction, 25% is due just to changing to electricity from combustion, and only 5% is end-use energy efficiency improvements, although you could get a lot more end-use energy efficiency improvements, which I'll talk about later. But why do you get this efficiency improvement? Well, you can see it in transportation the most. The plug-to-wheel efficiency of an electric vehicle is 80 to 86%. In other words, 80 to 86% of the electricity going into a car goes to move the car, and the rest is waste heat. An internal combustion engine, a gasoline or diesel, on average in the US, and this is average over all sizes, the tank-to-wheel efficiency is 17 to 20%. So only 17 to 20% of the energy in gasoline goes to move the car. The rest is just waste heat. It goes up to heat the car in the city. So you lose 4 to 5 times the energy, or you take 1/4 to 1/5 the energy by going to an electric car versus a gasoline car. And as a result, the cost of driving an electric car, the fuel cost, is 1/4 to 1/5. It's about 80 cents a gallon equivalent compared to $4 a gallon equivalent in the US for gasoline. So if you have an electric car and you drive it 15 years, 15,000 miles per year, you'll save $20,000 in fuel costs. And if the price of gasoline doubles to $8 a gallon, the price of electricity doubles, you'll save $40,000 over 15 years. So unless your electric car costs more than $20,000, more than the gasoline car. If you're just interested in saving money, you would want to go to the electric car. And there are a lot of electric cars that you can buy now that have a lot of long range, including like the Tesla Model S goes 310 miles on a charge that can be charged in 1 hour. But there are a lot of cars coming out as well. Now in the US, you would get a 37% reduction in total power demand by converting to wind, water, solar, because the US fraction of transportation where you get the biggest benefit is higher than in the world average. In Washington state, it'd be about 33% reduction in power demand. Again, this is just with only about 5% end-use energy efficiency improvement, so you could actually get more. But the goal now is, can we then power that 15 terawatts in the world with wind, water, solar, and the 2 terawatts in the US and the 0.04 terawatts in Washington state? Now I'm going to show for the world, my number is a little outdated because I have 2030 numbers, so this is how you do it for 2030 worldwide. One way. There's many possible ways. So that's for all purposes, again, electricity, transportation, heating and cooling, and industry. So one way would be with 50% wind, 40% solar, and 10% everything else. So the 50% wind worldwide is about 4 million large 5 megawatt wind turbines. And that sounds like a lot, but during World War II, the United States produced 330,000 aircraft in 5 years. The world produced about 800,000 in 5 or 6 years. Every year, right now, the world produces 70 million automobiles. So producing 4 million wind turbines, one time basically in 30 or 40 years, to power half the world for all purposes should not be that big of an engineering feat if we really put our mind to it. Now, so that's 50%. The solar is divided into rooftop solar, solar PV power plants, and concentrated solar power plants, and so that's 40%. And then hydroelectric would be about 4%, of which 70% is in place worldwide, 4% geothermal, and then a small amount of tidal plus wave power. Well, let's look at Washington State. Here's one way to do it for Washington. To power the entire state, and this is 2050 numbers, for all purposes, electricity, transportation, heating and cooling, and industry. So this would be mostly, well, there's 30% onshore wind, 13% offshore wind, 5% residential rooftop photovoltaic systems, 7% commercial government rooftop systems, 15% solar PV power plants. No concentrated solar power plants because it's more efficient to have concentrated solar with more direct sunlight, which you get in the more southern states and deserts. And of course, there are parts of Washington that do have really good sunlight. Seattle is not exactly one of them, but it does have good enough solar to have reasonable. I mean, Germany, for example, actually on last Sunday, Germany produced 75% of all its electricity from wind and solar. And most rooftops in Germany are covered with solar. They get a lot of rain, similar to Seattle. And so the latitude's even further north in most of it. So it can be done. It's just less efficient putting solar in cloudy areas. But you do get a lot of energy output. So you just need more panels. But remember, you don't, in a sunny place, it doesn't take up a lot of area to produce a huge amount of solar to power a lot of the US. So even if we had to double the rooftop areas that we covered or the power plant areas at some efficiency loss, it still can create we're still saving all that pollution and cleaning up the atmosphere and stabilizing energy prices. Now, so we wouldn't have any CSP plants. We'd have maybe 1% geothermal. 28% of Washington State would be hydroelectric powered. And almost all of this is in place. So we'd be adding in this, maybe it was round off air, only one new hydroelectric plant. So all of that 28%, almost all of it is here already. So we really need to power most of the rest of the 72% for Washington State. So it's actually, Washington State is probably one of the easiest states to do this in because the hydro is so useful because it serves as storage. Because as I'll show you, you want to balance the grid. the power demand on the grid. And so wind is intermittent, solar is intermittent, and when you combine them together, you do smooth it out, but you still have gaps. And the gaps can easily be filled by hydro, and that's what's done in California, for example. You fill in the gaps with hydroelectric. And when you have 28% of all your energy, electricity in this case, is hydro, it's pretty easy to fill in those gaps in Washington State. So you almost have a perfect system here, potentially, to set up. And then there's a tiny amount of tidal and wave power for 2050. Now, in terms of the areas, this is the areas required to power the entire state of Washington for all purposes in 2050. This would be new energy, so this doesn't account for existing hydro, for example. But the green would be onshore wind. That's the spacing area. That red dot is solar PV power plants. The yellow is residential plus commercial rooftop PV. That blue is offshore wind. Then there's a tiny amount of geothermal, that dot. So we're not talking about very much land area. This is clearly, for land area, the footprint is much less than 1% of the state, and the spacing area is around 2% of the state. So this would allow the elimination of all the fossil fuel infrastructure and the nuclear infrastructure too. So no more gas pipelines, no more refineries, no more gas stations, no more nuclear reactors, etc. Now, here's another scenario for California. This is powering California for all purposes in 2050. It would be mostly solar in this case, 55% solar, 35% wind, and the wind is 25% onshore and 10% offshore wind. Solar PV power plants would be 26%, CSP power plants 15%, rooftop solar would be 14% total. And this is covering virtually all south-facing roofs in California, plus parking structures. So there's not a lot more you can do on the rooftops. This, again, though, is for all purposes. So right now, if you look at the electric power sector, you'd say, oh, we can power a lot of California's electricity with rooftop solar. They could probably power about 60, 70% of it. But we're talking about converting everything else to electricity. So all the transportation is electrified, all the heating, cooling is electrified, all the industry is electrified. So then the solar becomes a smaller portion, the rooftop solar becomes a smaller portion of the total energy required, and therefore you have to go into deserts and use more wind, etc. But the land area for this is as such. It's similar in that it'll be, well, the red is the CSP plus PV power plants, the green is wind, onshore wind, the yellow is rooftop solar, the blue is offshore wind. And it's about less than 1% of the state for the footprint and about 2%, 2.5% for the spacing area. One more for New York, it would be mostly offshore wind, and that's the blue big dot offshore, and the blue onshore is onshore wind. The red big dot is PV power plants, and the red over New York City is rooftop solar, and similar areas. Now, finally, for the US as a whole, we actually did every single state, and we aggregated the numbers, and these numbers are as such. It would be 32% onshore wind, 19% offshore wind, concentrated solar and PV power plants, about 32% of the total energy, 2% geothermal, 11% rooftop solar, and 3% hydroelectric. But again, the total footprint area is on the order of 1% of the US and about 2% spacing area. So this again is to power the entire US, including Alaska and Hawaii, for all purposes with wind, water, solar in 2050. Now, what are the resources? So the US is blessed with great solar resources in every state. So even in the Northeast, which has the worst, which is the green, it's still pretty good. As I mentioned, Germany is even further north than most of the US and has their whole country is covered with solar and produces a lot of solar energy. And it'll just be maybe 20 to 40% more expensive in the Northeast. But in the Southwest in particular, you can see that it's really incredible solar resource. And in Washington State, it's mostly central, eastern, southern part of Washington. You have really good solar resources. Now, in terms of wind, the U.S. also has incredibly good wind resources on both coasts offshore and in the Great Plains area, but in a lot of pockets in between. And in Washington, actually I should have shown a Washington state wind map, which I have, but in the south central part of Washington state is where you have huge wind resources as well for the state. But I want to point out that worldwide there are about 70 to 80 terawatts of wind power available worldwide in high wind locations over land. And in 2030, you would need about 12 terawatts of end-use power for all purposes worldwide. And if we want to do 50% of the world, it's about 6 terawatts in 2030 that we'd need. But we have 70 terawatts of wind, so you can power the entire world for all purposes 6 to 7 times over with wind, and you can power with solar about 30 times over. So we have plenty of wind and plenty of solar to power the entire world, including in the US. Now, one of the impacts, well, we'd put up a lot of offshore wind turbines. In the plan I showed for the US map, for the entire US, it'd be about 20% of wind would be offshore. Now, if we put up, that would be equivalent to about 200,000 5-megawatt wind turbines offshore the East Coast a lot. We could also put them off the West Coast, but it goes deeper, so we'd want to wait till we have floating turbines for a lot of places, but there are a lot of shallow places as well. But the question arose, well, if you put up a lot of offshore wind turbines on the East Coast, wouldn't hurricanes damage them? So this became an interesting science question to answer. And actually my main work is to build computer models to simulate weather, climate, and pollution. So I happen to be simulating some air pollution, happen to be simulating, well, hurricanes, and also wind resources with this weather and climate model. And then the question came up, well, could you actually, wouldn't the hurricane, if it came by and you put up a lot of offshore wind, wouldn't it actually destroy all the wind turbines? And I thought, well, that's an interesting question. So I put these wind turbines in this computer model and simulated the impacts on hurricanes of large arrays of offshore wind turbines. And I found that, and here's a simulation of Hurricane Katrina. On the left is Hurricane Katrina on August 28th without any wind turbines. And this is wind speed. And on the right is when you put a large number of turbines to the southeast of New Orleans, and where that blue kind of wedge is. And you can see that the wind speed locally gets reduced by these wind turbines because they extract energy from the outer rotational winds of the hurricane. They convert, if you keep them on, keep them running, they'll convert that energy into electricity. Of course, people are running out of town, so the question is, what do you do with all that electricity? Well, that's an engineering question. So that's what the civil engineers have to decide. But theoretically, if you can use that electricity maybe to pump the water back from New Orleans back to the ocean, you can actually not only reduce the wind speeds locally, but that feeds back to reduce wave heights, which reduces convergence of air to the center of the hurricane, which then reduces the lifting of air in a spiral around the hurricane's core in the eye wall. That results in an increase of central pressure of the hurricane because you have less divergence aloft. So you actually feed back to increase the central pressure. That weakens the overall hurricane such that by the time the core gets to New Orleans, it's dissipated. So you can actually, with a large array, and this requires a large array of offshore wind turbines, you can actually dissipate a hurricane. And that's about, when I say dissipate, you actually reduce the storm surge by up to 80% and the wind speeds by like 50 to 60%. Now you could say, well, that would cost a lot. Well, actually, it wouldn't. It would cost nothing because you would put up the wind turbines to generate electricity year-round. That's their primary purpose. You wouldn't put them up to stop the hurricane. It just so happens that those turbines, if they're in the right place, would also reduce the hurricane risk. But they would pay for themselves by electricity sales over the year, and that's their design to be installed to pay for themselves. Whereas seawalls, which would, like New York was planning to put up $30 billion of seawalls for one city, and that would reduce the storm surge, but it wouldn't reduce the wind speeds at all, and it wouldn't pay for itself because seawalls don't generate electricity. So if you just instead took $30 billion and invested in offshore wind, then you can get that money back over time and reduce hurricane risk simultaneously. Anyways, just something for thought. So Walmart was really interested in this because Walmart has a new plan. They have a new goal that they're going to go 100% wind, water, and solar for all purposes, for all their stores. And they also need to reduce risk to their buildings because they have a lot of coastal buildings in the south and the southeast coast. So they thought, wait, with this we can actually solve two problems at the same time, save some of our stores and generate our energy. So they're really interested in this concept. But people ask, okay, well, let's go on to another topic here. What about reliability? The wind does not always blow, the sun doesn't always shine. Can you make this system reliable so that the lights don't go out? And the answer is really yes. But it takes work. In each location, you have to optimize it in a different way. This shows an example for California. I had a PhD student who spent 4 years studying this problem for California. And in this, what she did was develop an optimization model that tried to look at every hour over 2 years simultaneously. So we had the power demand in California for every hour for 2 years. We had the solar resources, the wind resources, the hydro resources, the geothermal resources. And so she converted, well, we used the same amount of hydro that we currently have and the same amount of geothermal we currently have, but just increased the wind and the solar and replaced all the fossil fuels and nuclear. And this shows two particular days. The black line is power demand over hour, that's the bottom is hour of the day. And the red on the bottom is geothermal power. That's supplied, there's kind of base load, so it's constant power during the day. The light blue is wind, and wind peaks at night over land in a lot of places in California. The yellow is photovoltaic solar. The orange is concentrated solar power, which you can use at night because you can store the fluid and then generate electricity at night with it. So that's why you have a little bit of orange at midnight on the first graph. And then the dark blue is hydroelectric, which was just used to fill in the gaps. And this is why you can see it's so valuable, because you can literally turn it off and on within seconds and fill in gaps in electricity demand. So on these two particular days, we were able to match the power demand exactly. And the gray was natural gas, which was backup, but was not used on these days. And in fact, it was found that for over 2 years, it was possible to match the power demand 99.8% of the hours over 2 years. Only 0.2% of the hours did you need the natural gas backup. And that was without even doing things such as what's called demand response management, where a utility will basically reduce rates to companies or individuals to not use power at peak times of the day. Just move it to nighttime or something. And so if you do that, you can actually shift the time of peak demand. And it's also without electric vehicles. When you have electric vehicles, then you can actually, that's what's called a flexible load. You can actually charge them at night or during the day. And so the utility can, again, give people a better rate if they charge during certain times of the day. So they use demand response management. And also, since we're going to electrify the entire system, the grid will not be anything like what it is today, because we're going to need electricity for hydrogen for some sectors. And also, like in Denmark, right now when we have too much wind or too much solar, and I think Washington State sometimes has too much wind because it's competing with hydro, it's just dumped, it's shut off. But in fact, you can use that extra electricity to either produce hydrogen or heat up cities. Like in Denmark, they have huge amounts of wind, and when they have too much wind, they just heat up the cities. It's called district heating. And so one way we can actually match the power demand better is we over-generate by installing more solar and wind than we need to match the power demand. And then when we have too much wind or solar, we take all the excess and generate hydrogen or heat the cities. And then hydrogen is another form of storage. So we have three storage forms, really: hydroelectric power, concentrated solar power, and hydrogen. And we haven't even talked about batteries, which are a third way of storage, which are more expensive. But that's also an additional storage, or flywheels, and there are other storage technologies. So anyway, the point is, there have been other studies that have looked at this and found similar things. You can do 99.9% of the PJM interconnect on the East Coast with wind, water, and solar, and using small amounts of storage. But it's really just an optimization problem. It's not an insurmountable problem. And in fact, I'll even talk about what's happening already in the US in a second, but let's just look at the costs of energy. Right now, wind is the least expensive form of electric power in the US, cheaper than natural gas. And when I say wind, Great Plains wind in particular. Like this year, just in the last few months, there have been 3 power purchase agreements in New Mexico, Texas, and Oklahoma, where wind cost is 2 cents a kilowatt hour. And that's the subsidized cost, so there's 1.5 cents per kilowatt hour tax credit, so it's 3.5 cents is the unsubsidized cost, and then you add about 0.5 cent for transmission. That's 4 cents a kilowatt hour for wind. That's the least expensive new form of electric power in the US. Now, if you do it in California, depending on where you are, it all depends on your wind location. It might be 6 cents a kilowatt hour, or in the Washington state, it might be 6 cents. But still, conventional fuels are about 8.7 cents a kilowatt hour right now in the life cycle cost. But they also add climate and health costs of another 5 cents a kilowatt hour, so they're really 14 cents a kilowatt hour. So right now, onshore wind, hydroelectric, and geothermal are cost competitive with conventional fuels. But offshore wind is more expensive. Concentrated solar power is more expensive. And certainly tidal and wave are way more expensive. Solar is coming down rapidly, but utility scale solar is almost cost competitive at 10 cents a kilowatt hour. But residential is on the order still of 15, 17 cents a kilowatt hour, so it's more expensive. But their costs, if you look at the trends in cost, by 2020 to 30, all the wind, water, solar options, they're all coming down in cost, whereas conventional fuels are all going up. So there's a crossover point. And it's already been met for wind, but not for some of the others yet. But by 2020 to 30, we expect conventional fuels to be 11 to 15 cents a kilowatt hour, whereas wind, water, solar will be anywhere from 4 to 10 or 11 cents. Now, you might say, well, wind, because people say, oh, wind is really expensive and it's going to cause people to lose a lot of money. But look at the actual data. If you take the 11 states, well, you wouldn't believe this, but 2 states in the US already produce 28% of all their electricity from wind. Anyone want to guess which ones they are? Yeah, Iowa is one. South Dakota is the other. Yeah. Yeah, that is true. That's 100%. Yeah. If you didn't hear that in the back, it was Washington, D.C. generates the most wind. Very good. A higher use by comedian. No, that's very good. But of the 11 states with the highest fraction of electricity from wind, the cost of electricity in those states actually slightly dropped in the last 5 years, whereas all the other states went up 8%. So you stabilize the price of electricity when you add wind because it has zero fuel cost. So you know what cost you're going to have going into it, because it's just all the capital cost that you amortize over time plus operation and maintenance cost, but no fuel cost. Now, but Hawaii you can see is a prime example. The cost of electricity now is 34 cents a kilowatt hour. The US average is 13 cents a kilowatt hour. Actually, Washington State has the lowest electricity cost in the US per kilowatt hour. But Hawaii has 34, which is the highest, and it doubled in the last 10 years from 17. Because you have to mine and transport fuels that are rising in cost. American Samoa actually is about 50 cents a kilowatt hour as well. And that's because you basically have to have diesel generators to generate electricity, so you have to ship over the diesel and then put them in the generators. So especially island places, this makes a lot of sense to try to go to local energy production, distributed and local energy production. But it also makes sense in much of the rest of the US. In terms of air pollution, as I mentioned, 59,000 people die prematurely. These are all ages. These are not just people who are weak and elderly. These are some young people as well, who are asthmatics and children as well. But this costs about $530 billion, or 3% of the GDP of the US for these health costs due to pollution. So this would be a savings by going to this plant. The number of jobs to put up this whole infrastructure by 2050 would generate 5 million jobs that are construction jobs over 40 years, and about 2.5 million 40-year operation jobs. This does not account for the job loss. The job loss, though, is a smaller number. I don't have that number handy. We're actually trying to get the exact number, but all indications are, we've done it for many states, and those states are virtually all gains, but there's some states that have losses. But it should be a net gain overall for the US in terms of jobs. And the transition timeline is as follows that we'd propose. And of course, it's not the only transition line, but it depends on if people are really interested in doing this. Well, the idea here is that by 2020, all new energy and transportation would be clean. So that all new vehicles would be clean vehicles, all new power plants would be clean. And that's not only to meet new demand, but to replace existing retired plants. And policies would be put in place to speed up the transition as well, such that by 2030 we would have changed 80% of the infrastructure, and by 2050 100%. So if we don't do anything, we go along the projected demand line on the top, and so our power demand goes up. The second line is the line that accounts for converting to electricity to reduce the end-use energy just because of the efficiency of electricity over combustion. The third line is to add additional end-use efficiency measures, and that would get us, and these include things that individuals can do, like changing their light bulbs, getting more energy efficient appliances, weather stripping their homes, going and just walking more, taking more public transit, bicycling more, things like that. Then we get to the 100% line, and that would be powered by hopefully wind, water, and solar. Now, so if I wanted to summarize kind of what I've talked about, this is really kind of a broad view plan that really requires that there are limitations to, including the main barriers are upfront costs, because a lot of this is capital intensive. I mean, wind, water, solar technologies, they have high capital costs but no fuel costs, whereas conventional fuels have lower capital costs but high and rising fuel costs. But there's also transmission needs. A lot of the energy we want is in places that are far away. These are not technical or economic issues, because like a 1,200 kilometer to 2,000 kilometer high voltage direct current transmission line from the Great Plains, or say Wyoming to California, it would cost about on average 1 cent a kilowatt hour when you amortize over the lifetime of the transmission, which could be 70 to 80 years, which is 2 or 3 generations of a wind turbine. And so that's not the issue. It's more the NIMBY issue that people don't want to add new transmission. So you almost have to go along existing transmission lines, and also to upgrading existing lines. But there's also lobbying and politics are barriers. But just to summarize, if we could get this plan working, in the US we would reduce about 60,000 air pollution deaths per year, saving $530 billion per year by 2050. $730 billion in climate cost savings due to US emissions alone. 5 million 40-year construction jobs and 2.5 million operation jobs, or gross jobs, not the net jobs. Because fossil fuel prices are rising and clean energy prices are dropping, the difference by 2050, if you extrapolate forward, is about $3,400 per year per person in 2050, another $3,100 per year per person saved in climate and health costs. The land area is about 0.65% of the US for footprint and another 2% for spacing. There are many ways of addressing the variability, and materials are not limits, but recycling might be needed for some materials. And then finally, I just want to point, if you're interested in more in papers and documentation on this and spreadsheets that have all the calculations, you can go to that website. I also encourage you to look at the Solutions Project website. And this is a group of, it's science, a combination of scientists and business people, and there are some policy people, but also artists and entertainers who are trying to get the information out to really educate the public about what's possible. So we've developed science-based plans. And by the way, these science plans for Washington State, the Washington State plan alone, we had 30 graduate and undergraduate students at Stanford helped to develop this Washington State energy plan that is on the top website. And there's a whole document on just Washington State. And so this was a volunteer effort by all of us. I mean, all the students volunteered their time to do this because they really want to help change. And this is great about a university to have such passionate students interested in making these changes. But the Solutions Project really is to take science combine science with business. We have a lot of companies that are really interested in helping instigate these changes as well. As I mentioned, Walmart, but also Google and Tesla and like Solar Mosaic and lots of solar companies, and Facebook has been interested as well. But an Apple computer also is going to large-scale renewable energy for a lot of its energy. So the Solutions Project is interesting. So I want to show you just a video, 2 minutes, that kind of hopefully will inspire you more. It kind of explains a little bit more about the Solutions Project.
So here at Shots of All, we trade in the currency of optimism. We're tired of doom and gloom, fatalistic thinking, the world is going to hell and all that. We need solutions to address the grand challenges of humanity. See, I believe in boundless possibility. Human beings are a curious species because we have the ability to conceive of delightful, exotic, future scenarios, and we can actually move the popular will. We can pull the present forward and meet and actualize any of those possibilities. That's what we do. We pull the present forward into the future that we create, that we map out. Today, we hear a lot in the media about the energy crisis. We hear a lot about sustainability. We hear a lot about strangleholding the planet. These are all legitimate concerns. But again, doom and gloom has been fatigued. We need solutions. So let's talk about the Solutions Project. The Solutions Project is an amazing new initiative led by Hollywood celebrities, brilliant civil engineers, the popular will of some of the smartest men and women in the world who have come together to leverage their brains to create a plan to take us 100% renewable here in America, literally 50 plans for 50 states by 2050 using technology that already exists today. The proposal is straightforward. Eliminate combustion as a source of energy. The sun gives us in one single hour more energy than we would need to power the Earth for a year. And the technology used to capture that energy is getting exponentially faster all the time. The fact that less than 2% of the United States land mass would support all of the wind, solar, and hydroelectric power generation required to meet energy demand is amazing. Now again, it all comes down to the fact that we need to make a cognitive leap. We need to realize that this is already possible now, today, with existing technology. You change minds, you change paradigms. So again, I encourage all of you guys to check out thesolutionsproject.org, get educated, get involved, join the conversation. Thank you very much.
Thank you all.